Alright, last video here in dealing with inference on a single population central value. Here we're looking at inference on a median. Alright, up to this point we have looked at inference on a population mean, but when the population distribution is highly skewed or very heavy-tailed, the median is more appropriate than the mean as a representation of the center of the population. So we're going to look at some inferential techniques concerning the median here. And so basically the idea here is that typically where this sort of technique would come into play is when you have a small sample and the evidence that the population that generated that sample is highly skewed one way or the other, then the t-test is one of the assumptions for the t-test is to have normal or near normal data. While the t-test is somewhat robust against departures from normality, if the skewness is heavy, then there can be some major problems with the t-test. And so it's good to have this kind of inferential procedure on the median in our back pocket. Here we go. The median. We're going to let the population median be M and the sample median be M hat. Okay? How do we compute M hat? Y'all have already computed the median, but here I have some notation to it. If n is odd, then the median, or the sample median, is y sub m. The m there is in parentheses. Now that y sub m, that's a special notation here. Y sub m is the mth ordered value. The mth ordered data value. And so the subscript is telling me where it is relative to the rest of the data. And if n is odd, then that subscript here, you should take the n plus 1 over 2 ordered data point, which is basically the middle of the ordered data if the data set is odd. If n is even, then m hat is the average between the mth and the mth plus 1 data point. Okay, ordered data points in the data set. All right, that's a point estimator. An interval estimator would look like this. It is a interval estimator for m, and the confidence level, now this is important, is at least 100 times 1 minus alpha percent, and it's given by this expression here. Y or ml is the lower bound, mu is the upper bound, but y with a subscript L alpha over 2 and y with a subscript U alpha over 2. Now, so I just need to figure out what is this L and what is this U. The L value is a C value plus 1. The U value is an N minus a similar C value. This C sub alpha 2 is a percentile from a binomial distribution with pi equal to 0.5. And those percentiles you get actually from table 4 in the back of your book. Okay. Now, because the confidence limits here are computed using the binomial distribution, which is a discrete distribution, it turns out the level of confidence, the probabilities, the way they work out here is they are discrete and they jump. And so the level of confidence here is generally somewhat larger than the specified value. So in particular, the exact the exact confidence level is given by 1 minus 2 times the probability of a binomial variable being less than or equal to this C value here. That's the confidence level. And this is not always 0.95 or 0.90 or 0.99, a nice value that we're used to, but we can get close enough to get some good confidence intervals on the population median. I'm not going to focus on this interval estimate on a population median in this setting here. I really want to spend some time on the hypothesis test in this setting. In this setting, it's called the sign test. And for testing hypotheses about M, we're going to use the binomial distribution to determine the rejection region using this procedure called the sign test. And the only assumption that we really have here is that Y is a random sample from a population and the median is designated as capital M. I'm going to let the null value of M be M naught, and I'm going to define WI as the data value minus the null hypothesized value M naught. And then I'm going to define B as the number of positive W's. Okay, so what is that? Well, B is simply, if you look at how W is defined, B is simply the number of data values that are greater than M naught. Now if M equals M naught, then there is a 50% chance that Yi is greater than M naught and a 50% chance that Yi is positive. I'm sorry, that Wi is positive. Now because the W's are independent and W has a 50% chance of being positive when M equals M naught, and since B counts the number of positive W's under H naught, B is actually a binomial random variable with pi equal to 0.5 and percentiles are from the binomial distribution. They can be used to construct the rejection region for various tests of hypotheses. So a hypothesis test is then constructed for M relating to M naught in this way. We look basically at B, which is the number of data points for which the number of data values bigger than M naught, and the rejection region is determined as follows. Now if we have a right tail test, that is, we have something that looks like this, the null hypothesis is that M is less than or equal to M naught, and the alternative is that M is greater than M naught. That's our right tail test. We would reject the null hypothesis and accept the alternative if B exceeded N minus C. Now again, this C value is from table 4, and we'll look at that in an example. Left tail test is reject H naught if B is less than C. Alright, and the two-tail test, you reject if B is less than C or if B is greater than or equal to N minus C. But now notice here the subscripts are different for the two-tail test, and that's taken care of in table 4 for us. So we can use this B value, the number of times or the number of data values bigger than M naught to perform our hypothesis test. Now one thing I do want you to be aware of, in the textbook in table 5.7 there's a comparison of powers for the t-test and sign test for different types of symmetry and skewness. So let's take a look at that momentarily. Okay, so looking at this table from our textbook here, you may want to read the background on where these values are being generated from, but just to be clear, the setting is we have 4 underlying populations that we're sampling from: a normal, heavy-tailed, light-skewed, and a highly skewed underlying population. Now if you're sampling from a normal population and you use a t-test statistic, and the level of your test, the significance level is 0.05, that is good. What this value is in here is the proportion of times in a simulation study that the test rejected the null when it should not have. Okay, and in fact in this simulation study, MA was equal to M naught in this row where it says level. Now as MA minus m naught over sigma actually increases, what that's saying is the true value of the median is different than the null hypothesized value. As that increases from 0.2 to 0.6 to 0.8, the power, this now becomes the power of the test. 0.145, the power of the test is 0.145, the power of the test is 0.543, and as that standardized difference of the two medians is 0.8, the power is 0.754. So you would expect to see, as this value gets bigger, the power would go up, and we see that with the t-test and also with the sign test. Now the power is a little higher here. Actually, I'm trying to highlight both rows. I don't think I can quite do that. There we go. The power is a little higher for the t-test than the sign test under this situation where you're sampling from a normal population. But if we sample from a heavy-tailed distribution, which is not normal, or take, for example, a highly skewed distribution, which is not normal, then the t-test actually has a level of 0.007, which is much lower than the specified nominal level of 0.05. And so that means it's rejecting at a lower rate than it has to of the false null hypothesis. And I'm sorry, it's rejecting at a lower rate of the true null hypothesis than is specified by the nominal alpha of 0.05. And so these values here reflect the power of the t-test, and the power increases. But if you compare the power of that t-test to the power of the sign test does much better. The powers are much higher in this situation where the populations are highly skewed. And you can look under lightly skewed situations where the underlying population is lightly skewed. The t-test is and the sign test are pretty close. Some instances one does better than the other, but they're pretty close. But under the situation where you have a highly skewed underlying population or a heavy-tailed underlying population, then the sign test may be more appropriate. But let's go back to our discussion on the sign test. So I'm going to go here back to our notes. Number 2 here in this note, often the sign test and t-test are both performed if there's some question about the normality assumption. And then also there's a section within our book, I'm not going to cover it, but large sample approximations for the sign test when n is large. You can take a look at that if you want to. Kind of my take is when n is large, then the central limit theorem is going to kick in, and the z-test should be appropriate in that sort of situation. So there's not this need to do this test on the median. Okay. Example 566 revisited. This is the data, the dissolution rates from before. And here we are going to test again the median dissolution rate. Well, I'm sorry, not again, but now I should back up. Now the parameter of interest is a median dissolution rate. So you may want to hit the pause button and read the setup here. But the median of the population M, so this is different than the mean potentially. It's the median dissolution rate of all pills in this batch. Now, to make I need to make you aware of this. Recall the picture of the normal distribution. If your underlying population is normal, then the median and the mean are the same thing. And so what that's saying is inference on the mean is the same as inference on the median if the underlying population is normal. And if that's the case, then the t-test is the way to go. But if the underlying population is not normal, if it's heavy skewed one way or the other, then the median is different than the population mean, and the median is a better measure to use for inference. Okay, and this method's nice too because it doesn't have a sample size requirement. All right, that's the parameter of interest there. The hypotheses are as follows: that M, the null hypothesis is that M is bigger than or equal to 20 versus the alternative that M is strictly less than 20. Okay, so moving on here, number 2, our test statistic in the distribution. Okay, the test statistic here is B. All right, and B is effectively the number of data points larger than M naught, which in this case is 20. Okay, so let's see. Well, we got one here, we got one here, one there, there, here, and here. So we have 1, 2, 3, 4, 5, 6 data points that are bigger than 20. That's my test statistic, and I'll actually use that in conjunction with table 4 in a little bit to make a decision. But that's the test statistic B. You recall is binomial. Here n is 24, and the probability of success in this setting is a half under H naught. Okay, so if H naught was true, we would expect half our observations to be above 20 and half to be below. That's why we use this B as our test statistic here. Okay, moving along here, number 3, I'm going to move to step 3. Step 3, the significance level alpha was specified to be 0.01, and the decision rule is going to be, we're dealing with a left tail test here, so we're going to reject H naught and accept the alternative if B is small, in the sense it's smaller than this C value, C sub alpha 1 comma n, and that C value is a percentile from the binomial distribution. And if you look this up in table 4, so let's go to table 4 here. So let's recall our alpha is 0.01, n is 24, so let's go to table 4 real quick. Okay, so table 4 is in the book, it's in the back of the book here. Okay, so here's table 4. I am looking for C alpha 1 n, so I'm going to be, this one deals with one tail test, and my alpha is 0.01, so here's 0.01, I'm going to be in that column, and the sample size n is 24, so let's see, I'm going to make this a little smaller here. Here's n equal to 24 there, n equal to, if I can, this doesn't highlight quite as well on a PDF. Anyway, n is 24, and alpha is 0.01, so my value that I compare B to is 5 there. Okay, so going back to the notes, reject H naught if B is less than or equal to, this is 5, and this is from table 4. Okay, from table 4. Okay, so now I actually, in step 4, I'm going to get ready to make a decision. Before I do that, I'll just make a statement about the assumptions. The assumptions that you need here are a random sample, and that's been assumed. That a random sample has been assumed, and we discussed that earlier. And so we're good to go with the sign test here. And next I'm going to actually compute my test statistic. This is pretty easy, right? We just counted the number of values that were bigger than 20, and our observed B was 6. There were 6 values bigger than 20. So we use that now to make a decision. Well, so is 6 less than or equal to 5? No, it's not. So we don't have enough evidence to reject the null. Our B is not small enough to reject the null. And so what we're going to do is we are going to fail to reject the null. So here we are in step 6, actually step 5 rather. Our decision and interpretation is, well, because B observed exceeds this C value, this percentile from the binomial distribution, we fail to reject H naught. Okay, so this concludes the sign test and the entire section dealing with inference on a single population central value.